All right, guys. Well, howdy out there to everybody at ScIC 4. Throw in the chat how many, if this is your first time attending, or if you've been to 1, 2, 3, or this is your fourth time attending. I'd love to see that. Oh, it's scrolling past. A lot of first timers, second, third. I saw fourth, first, second, third, fourth. Ooh, that's gone by fast. So I'm going to ask a bunch of questions to the chat, and I love this response. I'm going to have to work on my speed reading to be able to incorporate it into what I'm talking about today, but I love the engagement. So my name is Clifton Roozeboom. I'll be your host for the next 20 minutes, and we're talking about some of the amazing work that we did with StarTalk to bring 2 lessons into your classroom. One is what causes seasons, and we model that with some readily available things like a blow-up globe, a light bulb. And then we also talk about the discovery of exoplanets. So exoplanets being distant planets that orbit other stars, and how scientists discover those and how we can model that inside our classroom. So for any of the first timers that have never heard of PocketLab, PocketLab, we bridge the gap between digital and hands-on science learning. So we make things like sensors. This is our physics sensor called PocketLab Voyager, and this is what we'll be using today. We make other types of sensors. This is our environmental sensor called PocketLab Air. You can measure things in the air like CO2, particulate matter, ozone. We make apps. We do conferences like this for professional development and learning and just building a community. And then we also make lessons and activities, and I'll be showing you our cloud software where all of this is contained. So I'm gonna start to share my screen. I'll go kind of small in a window, and I'm gonna be interacting with a lot of stuff, but I also need to show you the digital side of things. So in your Zoom interface, there's a bar where you can kind of drag it and control the size. So if you want to shrink the share screen and make me a little bit bigger on your screen, there's going to be a lot going on over here. So pro tip for those new to Zoom. Okay. I am going to start sharing, so give me 30 seconds. And hopefully you can see this. So we introed PocketLab, and then next I'm going to pull up your chat, because I'm going to ask you guys a bunch of chat. And so what you're seeing on the screen is PocketLab Notebook. This is our cloud software for doing science experiments. Imagine it like a digital lab notebook where you have your physical notebook that you write observations down in. This is a digital version of that where you can add YouTube videos, you can add text, you can add data from your experiment live and in real time. And it's great right now because, as the poll saw from the attendees, a lot of us are teaching remotely or hybrid model. And so this enables that sort of collaboration even in these strange learning environments. So what you see here is PocketLab Notebook. And what I'm going to be using to collect data is PocketLab Voyager. What you see on the screen right now, it's measuring light. And we'll use this light measurement to talk about what causes seasons. So if I cover up the device, the readings go down. So this line graph is the time series of the measurements that we have. So I pointed sort of at some of my studio lighting here, and the readings will change. So that's what we'll see. And three takeaways for everybody watching this. We're going to have a meta discussion about the phenomenon, what causes the seasons. And I think this is an activity that probably all of us, or a concept that all of us learned at some point in our schooling, maybe multiple times. But the understanding of what causes seasons are, it says something about how we understand models and what sticks with us in science education. So All models are wrong. Some are useful. This is a famous quote by the statistician George Box, and we'll dive into that. And that's what we were talking about with Neil, understanding, how are they useful, where are they limited? And then the two lessons that we've done with StarTalk and Neil cover what causes the seasons and how to discover an exoplanet. So, Robbie, if you can put up the poll for the audience. And the first poll I want to ask everybody is, to your understanding, what causes the seasons? So there's answer choices A, B, C, and D. And let me explain it. A is the Earth moving closer and further away from the sun during its elliptical orbit that varies with the time of year. So the distance from the sun, essentially. B, the Earth rotating on a tilted axis such that the amount of sun hitting the northern or the southern hemispheres varies with the time of year. C, I got this from the Flat Earther wiki page. The Earth is flat, and the orientation of the sun orbiting the North Pole varies with the time of year. I didn't know that. That's how you explain seasons if you're a flat earther. And D is none of the above. Maybe we didn't capture the real reason. Okay, so I can see the poll questions coming in, poll results, and I'll stop it now so you guys can see the results. And our audience is really smart. The correct answer is B. 78% answered that, gave the correct answer. And then the most common misperception is answer A, that the Earth moves closer and further to the sun depending on the time of year. So 78%, that's a large portion of people that understand this correctly. And why do I say that? Well, there's a pretty famous study in 1987 done by the Harvard-Smithsonian Center for Astrophysics. And what they did was they went around Harvard on graduation day and asked 23 recent Harvard grads this same question: what causes the seasons? And of the results, 21 out of the 23 Harvard grads incorrectly answered. And then this same research group has done further studies estimating that 95% of the general public cannot correctly explain this concept. So our poll results show that this group of people is way smarter than a bunch of Harvard grads. And why is this misconception so pervasive in a concept that we've probably all learned at least once, maybe multiple times in class? And the authors of the study, Philip Sadler, one of the authors, is saying, well, it turns out that for most major scientific concepts, students, kids are coming in with a whole set of beliefs that are commonly at odds with what scientists and science teachers know to be true. So even elementary school, middle school students are coming in with concepts, pre-held concepts that we have to battle and correct as science educators. So, I mean, it starts maybe earlier than we would realize that, middle school students have a very pre-cemented idea of how some of the things in the world work. So, another audience poll. Robbie, if you can relaunch the poll, and I'd love to see for attendees, have you ever taught this concept? So answer A, yes, if you have, or B, no. And then we'd love to see as you guys respond in the chat, if you have taught this concept, at what grade level, and then how did it go? So I see from the poll results about 65% of the attendees have taught this concept. 5th grade, 6th grade, 7th grade, 9th grade, 3rd grade, going by really fast. Middle school, 5th, 6th, 9th, 11th, 6th. Community college I saw, 7th, middle school. I saw 1st grade. So, it gets taught over and over and over again, or it gets taught at different grade levels depending on where you're at. And from the poll results, looks like about a third of our attendees haven't taught it, and about 2/3 have taught this concept. So, this is pretty foundational, one of those classic science experiments that everybody does. And let's talk about sort of the modeling aspect of it. So if you're in the US and you're in a state that has adopted the NGSS, Next Generation Science Standards, you may or may not know that part of those standards are an emphasis on what are called science and engineering practices. If you're international, which a lot of our attendees are, maybe you've heard of the NGSS, maybe not, but this is the US's attempt at sort of standardizing the way that science is taught and the concepts that we cover. So there are 8 science and engineering practices, and these are ways that we want to train students in how scientists and engineers actually do their job, go about problem solving. And for developing and using models, this is SEP2. For kindergarten and second grade, these are simple models, diagrams, and drawings, and the analysis kind of comes down to comparing and contrasting those models. But even by third grade, you're building models and then identifying the limitations. So how does this model break down? Where is it wrong? How is it useful and where is it wrong? And then in middle school and high school, your models get more complex, but then it's sort of in the standard to evaluate the limitations of these models. So going back to that quote that I mentioned from George Box, that all models are wrong, some are useful, from the time that our students are third grade, we're supposed to be emphasizing that first part, that these models are wrong and we need to understand how they're wrong. So like we teased earlier, PocketLab and StarTalk got together and we recorded some demonstrations and did some experiments. Myself, Neil, and Chuck doing modeling what causes the seasons and teaching that in a way that we think is fun and with your students, useful from like an upper elementary school to a like 9th, 10th grade high school level. And Neil, the master teacher that he is, starts with the phenomenon, takes us through personal experiences that really cement our understanding in what happens in the world around us. And then we dive into the model and show how our model is useful for this concept. So he gives a master class on how to teach this concept. And you can access it by signing up for the PocketLab Notebook. So if you go to thepocketlab.com/app, this lesson and Neil's lesson on discovering exoplanets are available for you to use. It's free to access and try out. So not right now while I'm talking, but as soon as this presentation is over and during our break, go sign up on our website, thepocketlab.com/app, and you can access these lessons. So we should collect some example data and take a look at the model that we used in this activity. So in a different tab on my browser, I already have fired up my PocketLab. And so my PocketLab is going to be used to measure light intensity. I have here my light bulb, which will act as the sun. And then I have here a very inexpensive blow-up globe with some tape on it. If you have a nice globe on a stand, that's terrific. It'll probably work better than this, but you can do really cool modeling and an intuitive understanding of what's going on with very inexpensive tools. So I'm going to start the nuclear reaction in our sun. You may have seen the light intensity jump up on our screen coming from the PocketLab. We'll turn off the house lights so it makes it a little bit darker. And then in this activity, we look at, here's our sun, here's our Earth. We could put a measurement light meter here, let's say in St. Louis, here in the Northern Hemisphere. And then looking at as the Earth orbits around the sun, it is at a tilted axis of 23.5 degrees off of vertical. And this axis, relative, like in the universe, stays pointed in particular direction. So in the summer, in the northern hemisphere, this axis is pointed towards the sun, and it's kind of hard for me to get across over to winter, but imagine we just went over to winter. Our axis would be then, the axis would be pointing away in the northern hemisphere, and the southern hemisphere would be pointing towards the sun. The Earth being off axis by about 23.5 degrees. And we go through this activity, collect experimental data. So it's a little hard for me to stay on camera, but looking at the light intensity when we're at one position relative to the sun, and the data on the screen is showing light in terms of units of lux. Lux being a measure of the visible light intensity. And then you can reorient your solar system model and rotate your setup, and then look at how this changes during different seasons and position of the Earth. Okay, so that's the activity. Go create an account so you can check it out. And I would love to see and respond here in the chat. That question that we're trying to get at. Pros: how is this model useful? And then cons: how is this model wrong? And I'd love to see your thoughts from people that are in the classroom. So just as the chat is going in, go ahead and put pros, how this is useful, cons, how it's wrong. And this isn't a poll question, but as the chat's going through, I'll check out and sort of read that. So one way, I'm going to turn my son away. So one way that we are incorrect in modeling these relationships are, obviously on the scale of things. So this picture right here shows, the sun and the Earth in accurate scale. So there's the sun, and if you can see the tiny little blue dot, there's the Earth. Obviously, this being our sun and this being our Earth, we're totally out of whack on that scale. Even more out of whack is sort of the relative distances between these things. So if on your screen that sun is 4 inches high, then the Earth, the little teeny tiny blue dot, would need to be 36 feet away for us to be in scale. So obviously we can't do this in a classroom. We can't have students 36 feet away from each of their lab stations. I think we'd have to do this in the gymnasium. So understanding, where we have to give up on accuracy in terms of things like the scale, what Neil was talking about earlier, the scale of maps is a good example as well. That's a breakdown in our model, and it's a breakdown by necessity because I don't have a sun that's the size of a football field to match my globe that's the size of a beach ball. So yeah, a lot of great advice here in the chat. Pro measuring and seeing change in the temperature. Sort of the comprehension is a pro of this model. Cons is the scale is way off, way off. So that's what we're tackling with these two lessons: is the pros and cons of modeling. How can we collect data from that? And then just to tease our other lesson, here is how to discover exoplanets. And we do a very similar sort of modeling approach, talking about first the phenomenon, then experiences that we can draw from, and then going to the model. So in this case, we're looking at planets that are far away, orbiting distant stars, and how with telescopes like the Kepler Space Telescope, we can discover those planets. So in the second lesson, we use our light bulb, this time as a distant star. We use PocketLab Voyager as a space telescope, and then we set up a record player and have different planets orbiting our distant star and collect experimental data from that. This another terrific sort of way to look at models and ground them in, real experiences, like real activities that scientists are doing, and that's, looking at distant galaxies, trying to find other planets. So, if you didn't take away this already, you can access these lessons for free on the PocketLab Notebook. So if you go to the PocketLab.com/app and sign up there, you can start to check out these 2 lessons. And there are activities that cover a wide range of other models and other experiments, ranging from upper elementary, like 3rd, 4th grade, on up through university education. So we're really proud of these things. Let me tell you, Chuck and Neil are, to learn from them, and do an activity that your students can do the same thing that they're doing, is we think a really fun experience, and it'll get your students fired up. So check that out. Sign up during the break while you have sort of 10 minutes of downtime, and we'd love to know what you guys think, and so we'll be in correspondence with all the attendees and everybody here. So I think I see Dave pop on the screen. Let me stop my screen share.
Cliff, that was great. Thanks. Thank you so much. Let's do some questions from the chat. The first thing, though, I got to tell you what I learned is, did you see the poll? So most of the teachers knew the right answer to why we have seasons. So here's what I learned is that the average science teacher is way smarter than the average Harvard grad.
Yeah, 100%. It's not even, not even close. Yeah, it was 5%, or 5% correct for Harvard grads, and we're like 78%. So it's, like 15-fold smarter.
And, I think the other thing, the other part of that article, even some of the faculty got it wrong.
Yeah. So of the 23 people questioned, 3 were faculty, and I don't know, they didn't specifically call out the faculty, but at least one of the faculty had to get it wrong because only 2 people got it right.
Yeah, that's pretty funny. So next time we have Robert Liu from Harvard on, we'll bring up that.
Yeah, we'll give him a hard time.
So there's a ton of questions. A great question I saw was, you can use these 2 lessons without sensors, right?
Yeah. So there's example data in there already. You can do it qualitatively. So, it's nice to have a light sensor, but you can look at the shadow that's being cast over the Earth, get a sense for orientation and things like that. If you have, implements, but that's also shown in the video. So assuming your students are at home and they don't have a blow-up globe, you could still do it. And then when you get back in the classroom, you can do this in a demo form, and use Neil and Chuck to augment what you're doing in front of the students.
Yeah, so for those, Cliff pointed out, you can go log into Notebook, and I see that Scott is putting the links in, other people putting the links in. It's free. You need an email to sign up, but these lessons are free, and they're great lectures. They're like 15 minutes long, and you really have Neil like going into the phenomena and the details. They're actually quite interesting.
Yeah, I mean, and Chuck keeps it light and brings the fun.
Yeah. So on the let me see, looking at the chat really quick here. So log in, you get the lessons for free. They dig into the phenomena. There's 2 lessons on there. And international, there's no issues. International, obviously, it's software. Yeah. So what was interesting is the talk about the models, and I see people here thinking models need to be rethought. So this is something I think we want to try to help tackle too. Is what are the best models, and we'd love to have teachers share these on, for example, on the Facebook group, share their models, and we can kind of go through and get people's comments on them.
Yeah, yeah, we can have a rate my model response on our Facebook group.
Yeah, by all means, go to the Facebook group, show the models you're using, and go, and see what everybody thinks about them. So, we're just at the break. Cliff, any final things you want to bring up?
Well, the work that you science teachers do is tough. You're with students maybe for a year, and you're trying to, dealing like the researchers say that there's a lot of preconceived notions that students bring in with them. So understanding what those notions are, and then how you can reorient them to be more scientifically accurate, and understand those skills like these science and engineering practices of building models, and then really critically looking at them and understanding where they're good and where they fail. It's a really tough task, and it's each teacher, I think, carries the ball forward for the year maybe that they have their students, and it's up to us, as a community to kind of bring them along when they go from elementary school to middle school to high school, to understand these limitations and the power of models, a little bit better each year. So it's a tough task. It's a big challenge for us educators, this community, but it's something that we want to be providing tools to make a little bit easier.
And Cliff, there's kind of an important thing, I think. So we had great fun, obviously, recording these with Neil and Chuck. And Cliff is the star of the show with those guys. They're fun to watch. But there's one thing that I noticed. You don't need a lot of equipment to do this. So basically, Cliff had the globe and the sensor, and then everybody else was in the audience, like students. So it's almost as if he was giving a WebEx or a Zoom class, and the students could see the data, they could comment, and so on. So it's actually, it would work in a remote situation pretty well.
Yeah, and Neil relies on some physical, intuition, and hey, you be the planet and you go off axis at 23.5 degrees, and it's this modality is a learning. For us to talk at the student and describe the model is one way, and then for them to see it is another way. And then if they can move their bodies or play with the globe and move it around, that's yet another way of learning and understanding. And we try to hit a bunch of those methods.
This is great. Cliff, this is awesome. Thank you so much. We're a couple minutes into the break. I apologize for that. We'll keep things back, get things back on track. So the next session starts at 10:40 Pacific time, so in 7 minutes. And next for you, we have Lego, which is going to be great. They have a really interesting presentation for you. A few people asked, where is the schedule? So there's a website. We'll post it in there. It's ScIC-conference.com. If you just go to that website, it has the day schedule. You can keep an eye on it there. We will be posting all the links, so don't worry. The best place to get them is on the ScIC Facebook group. I see somebody posting that there. And the other thing, a lot of people are asking about the videos. We are recording those videos. We will send them out after the conference, but I'll tell you where they're going to be. We have created an ScIC YouTube channel. So you should all right now go there. We'll put the links in here. Let's see, somebody posts it. And you can subscribe and click the bell, and you'll get a notification when the videos go up there. So that's the best way to get the segments from this. And we're going to put the prior conferences. We're just putting it up there right now. So let's see if somebody puts up there it is, YouTube channel. So go check out our brand new. We just launched it today. You're the first people in the world to see it. So thank you for asking that question. That's a great question. And we'll post everything there. So we're going to go to break. Cliff, thank you so much. That was fantastic. We're going to go to break for 5 minutes. We'll be right back. And I see Lego is on, and we're going to start promptly at 10:40. Thank you.
Thanks, teachers.